to become the next Sir Isaac Newton or Albert Einstein? Learn from the master, Refath Bari. Watch his videos to achieve your dream.
Lecture of linear algebra. For the last few lectures, we've been talking about the null space and various other important subspaces of any matrix. Today, we're going to switch gears to what I like to call orthonormal matrices, okay? So, our exploration of orthonormal matrices are going to begin with rotational matrices, which are rigid transformations. So, let's go ahead and take a look at the do now. The do now will test your understanding of what a rigid transformation even is, okay? So, and of course, feel free to comment down below if you have any questions or comments. And let's get started. Okay, so let's see. Identify, or I don't know, pick. It's an easier word. Pick the rigid transformations. So rigid transformations. Okay, so I'm just gonna give you like 2 or 3 transforms, and just go ahead and pick which ones seem rigid. Okay, so first one is gonna be a square, and it's rotated by its center, around its center, by 30 degrees. So this will be the resulting square. I guess it'll look like a parallelogram, not 100% sure. But there you go, that's a square. Next thing we'll have is a circle, a concentric circle that is dilated by 2 times its original size around its center once again. And let me just dash that out so it seems like a transform. Okay, and what's the final thing I want to do? The final thing I want to do is, let's do a triangle. Doesn't hurt. A triangle, and I'm going to rotate my triangle 30 degrees around one of its vertices. It doesn't have to be 30, it could be 50 or whatever. Okay? So you can almost think of this as a reflection. Okay, so any ideas which one of these are rigid transforms? Audience, feel free to just shout out A, B, or C. Huh? Which one of these are rigid transforms? Any guess? Huh? Oh, we have a guess. Yes, that's right. It is A and also C. So good catch, but you missed C, not just A. Now, why are these rigid transforms? Why are A and C rigid transforms? Simply because we are rotating these diagrams, right? So for example, this one I rotated by 30 degrees, and this one I rotated by something like 45 degrees. But at the end of the day, a rigid transform is simply a transform that preserves the side length of the original picture. Okay? As you can see here, we don't preserve the size of the original circle, whereas here, in these rigid transformations, which you can categorize as rotations, the size of the shapes remain the same. Okay? So that's what a rigid transform is. So let's go ahead and take a look how we can derive the rotational matrix for a rigid transform. Okay, so that's going to be our lesson today. My eraser may be out of date. Okay, so let's see. In our lesson, we're going to explore the rotational matrix. Okay, so when I think about rotational matrix, what I like to think about is just the good old 2-dimensional coordinate plane. So that's exactly what I'm going to draw right up here, right now, as soon as I can get rid of these marks. Okay, so let's see. What I have here is 2-dimensional coordinate plane. What am I going to do? I'm going to draw, I don't know, I can say a segment there, and I'll draw another segment here. And I'll say that both of these segments, okay, both of these segments are going to lie on some circle. Maybe it's even a unit circle. So, you know, these segments might both be unit vectors. Well, that doesn't have to be the case. I'm just trying to keep things easy here. Okay, so let's say the angle between these two vectors is alpha, and we can give each of these vectors some random coordinates. Maybe I can call this, let's call this A, and let's call this B, and let's call the coordinates of this one A prime and B prime. Okay, now when we want a rotation matrix, basically what we want is some kind of linear transformation that's going to take us from vector.
Is it 74?
Yes. So, good catch.
What is the topic?
The topic is rotational matrices.
Can you write it down?
Rotational. Let's go ahead and write that down. Rotational matrices. Okay. Don't worry, this is all going to tie into our discussion of subspaces and column spaces and null spaces. Okay. So back to what I was saying, which is our goal is basically to derive a linear transformation that takes us from this vector AB to the second vector A prime B prime. So how do we get such a vector? Well, the first thing I'd like to do is go from my good old Cartesian coordinate plane to the polar coordinate plane. Okay? So first and foremost, let me write down my goal. My goal, hopefully you see that right there. So what is my goal? My goal is to get a transformation T such that, when I input this vector AB into my transformation, I get an output of what? I get an output of A prime B prime. Okay, so that's my goal, to derive that some kind of linear transformation that does the job of rotating a vector for me. So as I said, the first and foremost step is to convert from rectangular to polar coordinates. So what I'm going to do to that end is go ahead and write down what I think are the right polar coordinates. I'll write down A is r cosine alpha. Does that make sense? Actually, it doesn't make sense because we have to introduce a new angle, theta, right here. Okay, so now I can just go ahead and write r cosine theta, and B is equal to r sine theta. Now go ahead and think for a moment why that makes sense. Why that makes sense is because A is the x component of my vector, and when I'm converting to polar coordinates, of course the x component is going to be represented by the trigonometric function cosine. Right? So hopefully that makes sense for you right there, and I've drawn a visual aid so that it helps clarify things. So that right there is going to be my r cosine theta. And of course, likewise, this is going to be my r sine theta. Okay? Now, what are we going to do to achieve that linear transformation that's going to take me to A prime B prime? What can I do from here on? Well, first and foremost, let me go ahead and write these. So I'm going to write A prime is equal to and B prime is equal to. Now think about what's happening here. A prime, if you look at A prime and B prime, they're just this vector but rotated by a couple of degrees. In fact, rotated by an angle alpha. Okay? So what I can say is that A prime is simply r cosine of no longer theta, because we no longer have an initial angle of theta. Instead, we have theta plus alpha. So let's just go ahead and write that down. Theta plus alpha. And of course, I'm going to write my alpha as A. Common mistake. So hopefully you see what I've written down there. And likewise, instead of r sine theta for B prime, I'm going to write r sine theta plus alpha, because of course I have that extra angle. Okay? So hopefully that makes sense. Okay. Now what I'm thinking to do is simply go ahead and expand this using my simple knowledge of trigonometric identities. So what does my cosine addition identity tell me? Well, my cosine addition identity tells me that the cosine of the sum of two angles A and B is simply going to be what? And actually, I don't want you to confuse A and B with what variables I have here, so I'll call them, I don't know, E and F. Right, so what is the cosine of the sum of two angles? Well, I can just go ahead and write it down. It's going to be cosine of the first angle times cosine of the second angle, but instead of adding it with sine of each of these angles times each other, I actually have to subtract it. So minus sine of E times sine of F. Okay? So that's just a common trigonometric identity that we need to derive this transformation matrix. Okay, but we're not done. We're not done. We still have some ways to go by deriving or extending the sine identity right over here. Okay, and that's exactly what I'm going to do in today's exit flip. Okay, so as part of our exit flip, our goal right now is, well, during our lesson, we actually went ahead and converted. What did we do during our lesson? We drew a diagram of the desired linear transform. We converted from Cartesian coordinate plane to polar coordinate plane. And then what did we do? We went ahead and used one of our favorite trigonometric identities, which is the addition of the sum of a cosine of an angle. And we expanded that as
sorry, I just joined in the middle of class. I was with me.
no problem. And so now during our exit step, what I hope to do is just go ahead and expand this one right here, right now. Okay, so what does my sine addition? Let's wait for that to pass. What does my sine addition property tell me? My sine addition property simply says that the sine of the sum of two angles is, well, I think you guessed it by now, the sine of the first times the cosine of the second plus sine of the second. Of course, I messed it up. Plus sine of the second, sine of the second angle times cosine of the first.
Close.
Okay.
Close.
So that's it for today's lesson. We've gone ahead and expanded our two trigonometric identities, and we've just accomplished the first step towards deriving the rotational matrix. So this is only the beginning. We're not even there at the meat of the problem yet. So thank you for watching. If you have any comments or questions, leave them down below, and we'll see you in lecture number 75.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.